Okay, now let's move on to on to the next problems. On problem number 27, all you need to do is simply show me that you understand the rules of making rectangles in Karnow maps. And the idea here is just show me the best possible set of rectangles you can come up with. You don't need to come up with the expression at all. So this is just a matter of making rectangles. Now my suggestion to you in class was to simply start out with just one of the ones, and make the largest rectangle you can possibly make. Now the key behind these two X's that you see in this Karnow map is that those are wild cards. You can make them a 1 or a 0, whatever makes for the best possible rectangle. So if we start in with this 1 in the upper left hand corner of the Karnow map, I can't pair it with the one that's to the right of it, or the 0 that's to the right of it. I can't pair it with by going around to the opposite side because there's a 0 there, but I can pair it with the one below it. And so those two ones, by putting those two ones together, I will double the size of the rectangle and drop one variable out, so I'll only have 3 variables in the term. Now right below those two ones you have an X. If I make that X a 1, then that 1 now allows us to make this entire column one rectangle. And by making that entire column one rectangle, I have made it a rectangle of size 4 allows us to have 2 input variables drop. And that requires that we make this X right here a 1. Now that's as big as we can make that rectangle. I can't double it to its left, I can't double it to its right, so we move on to the next one. So there's a 1 here that's in that the top one that's in the column on the right hand side. Let's see what rectangle we can make around that. I can pair it with the one below it, making a rectangle of size 2. If I pair these two together, can I make a larger rectangle? Well, it turns out I can't go to the left because I'm blocked by the 0, but I can go all the way around to the opposite side and make a rectangle there of size 4, once again allowing two variables to drop out. That's the biggest rectangle I can make out of those guys. Now next I've got this 1 all by itself in the third column, third row. Now that 1 can't be paired with the 0 that's above it, can't be paired with the 0 below it, or the 0 that's to the left, but there is a 1 that's to the right that it can be paired with, and that's the largest rectangle I can make around that guy. Now I've got all my 1's covered, so as far as the X's are concerned, all the X's that are not covered by a rectangle need to go ahead and be set to 0. And so that's the pattern of 1's and 0's, or excuse me, that's the pattern of rectangles that you would get for problem number 27. Now moving on to problem number 28. Now number 28 is a matter of, do you understand how the sum of products expressions, how each of the products in the sum of products expression affects the truth table? Let's start out with this first product right here, A bar ANDed with B. Now what I need to know is what values of A, B, and C will make that product equal to 1. Because if A bar and B is equal to 1, we're going to get a 1 in the truth table. So when does A bar B equal 1? Well, A bar B equals 1 when you get a 1 ANDed with 1. That means B needs to be a 1 and A bar needs to be a 1. A bar being 1 means that regular A, non-inverted A, needs to be a 0. So A is a 0, B is a 1 will output a 1 for the product A bar ANDed with B. But C is not in that expression. So C can be anything at once, a 0 or a 1, whenever it comes to making A bar B a 1, that product a 1. So we actually have 2 rows in the truth table that are going to have 1's generated in it by this product. The first row is going to be A is 0, B is 1, C is 0. So 0, 1, 0. We get a 1 in the truth table for that product. The other row that's going to be have a 1 placed in it by having from this product is when A is 0, B is 1, C is 1. So 0, 1, 1, that's also going to have a 1 in it. Now let's move on to the next term. A bar ANDed with C bar. For what values of A, B, and C will A bar C bar equal a 1? Because when A bar C bar is equal to a 1, we know that the whole sum of products expression is equal to a 1. Well, A bar C bar is equal to a 1 when A is equal to a 0 and C is equal to a 0. B can be whatever it wants. So once again, we're looking at two rows in the truth table being affected by this product. The first row is the 0, 0, 0 row, and the next row is the 0, 1, 0 row, which already has a 1 in it, so we won't add another 1 for that. And that takes care of the A bar C bar product. The last product, A B bar C, when is this guy equal to a 1? For what values of A, B, and C is this one equal to a 1? Well, the product needs to be 1 ANDed with 1 ANDed with 1 in order to generate a 1. So that means A needs to be a 1, B bar needs to be a 1, which means B needs to be a 0, and C needs to be a 1. So that generates 1, 1 in the truth table at 1, 0, 1. Now, if a 1 is not generated by any of these three products, in other words, all three of these products are equal to 0, then 0 or 0 or 0 is equal to a 0, and all the rest of the rows of that truth table are going to have zeros in them. And that takes care of problem number 28. Now, problem 29 is asking for making sure that you can make a decoder that is active low. Well, decoder is an AND gate. An active low decoder makes it a NAND gate. All right, so the circuit itself is quite simple. It's just a NAND gate, an AND gate with an inverted output. But we need to figure out how A, B, C, D, and E are connected to this NAND gate. Any of the inputs that we're looking at that need to be set to 0, in an AND gate, the AND gate is looking for 1s. And so what we're looking for is A bar is equal to a 1 and E bar is equal to a 1. So you'll have A bar is equal to a 1, B is equal to a 1, C is equal to a 1, D is equal to a 1, E bar is equal to a 1. So both A and E need to be inverted before going into the NAND gate. B, C, and D all just go straight in. And let's look at problem number 30 now. Problem number 30 once again says, I'm just asking if you know how to take the values from the rows of the truth table and put those in the location of a properly drawn Karnow map. Now, a 8-row truth table is going to have an 8-cell Karnow map. And you could draw it so that it was horizontal, but convention makes it so that we can make more rows than we'll make columns. And the columns are going to be identified with the 4 possible combinations of A and B, and the columns are going to be identified with the 2 values for C. So the rows, the values of A and B would be 0 and 0, 0 and 1, 1 and 1, and 1 and 0. Now this numbering here is that gray code. And remember, it has to be gray code because neighboring cells on the on the Karnow map have to differ by only one input variable. So, and the columns are going to be identified by 0 and 1. And so each one of these cells corresponds to exactly one row in the truth table. So for example, this first row right here corresponds to when A is a 0, B is a 0, C is a 0. And that is this top left-hand cell here. So this 1 that is in the top row goes right in that position. The next cell, this cell right here, the top right-hand cell on the Karnow map corresponds to 0, 0, 1. So 0, 0, 1. So this one right here goes in that position right there. The next cell, A is 0, A is 0, B is 1, C is 0. 0, 1, 0. This 1 right here goes in that position. The next cell, 0, 1, 1. A is 0, B is 1, C is 1. A is 0, B is 1, C is 1. That X goes in that position. Now because of the gray code, we have a funny hop in the truth table. The truth table you don't just simply number the truth table exactly the way that you number the Karnow map. There's that gray code consideration. And so the next cell in the Karnow map corresponds to A is 1, B is 1, C is 0. So we jump down to A is 1, B is 1, C is 0, and this 0 goes right there in the Karnow map. The next cell corresponds to A is 1, B is 1, C is 1, and that's the bottom row of the truth table, so that X right there goes in that position. Lastly, the bottom row of the Karnow map. Bottom row of the Karnow map is identified by A is 1, B is 0, and the leftmost cell is C is 0. So A is 1, B is 0, C is 0. That 0 right there goes in that position. And lastly, the last cell on the Karnow map, 101, 101, that 1 right there goes in that position.